The universe is whispering to us, and some of its most mysterious messages come from dying stars. Imagine a cosmic lighthouse, pulsing with signals that defy explanation. Signals so strange they leave even the brightest astronomers scratching their heads. These aren't just any stars, they're red giants, massive celestial bodies in their final fiery acts, and they're sending out patterns we can't yet decode. Some flicker like a candle in the wind, others vanish without warning, and a few even seem to repeat in ways that mimic intelligence. What if these aren't just random stellar tantrums? What if they're clues to something far bigger, something we're only beginning to grasp? Today, we're diving into 25 of the most baffling signals from red giants across the cosmos, signals that challenge everything we know about how stars live, die, and maybe even communicate. Strap in, because the universe has secrets to share, and you're about to hear them. Now, let's turn our attention to one of the most famous red giants in the night sky, Betelgeuse. This colossal star, part of the Orion constellation, has been acting strangely, and its unpredictable behavior has astronomers buzzing. Unlike most stars which follow steady rhythms, Betelgeuse pulses erratically, as if it can't decide how bright it wants to be. One of the most baffling moments came in late 2019, when Betelgeuse suddenly dimmed by nearly 2/3 of its usual brightness. For months, it flickered like a dying light bulb, leaving scientists scrambling for explanations. Some thought it might be a sign that the star was about to go supernova, a spectacular explosion marking the end of its life. Others suspected something less dramatic but equally puzzling, like massive dust clouds obscuring our view or deep-seated changes in the star's outer layers. What makes Betelgeuse stand out isn't just its size. It's roughly 1,000 times the diameter of our Sun, but the way it defies expectations. Most red giants pulsate in predictable cycles, but Betelgeuse dances to its own chaotic tune. Some astronomers believe its erratic signals could be caused by massive convection currents bubbling up from its core, while others point to magnetic field disruptions or even the influence of an unseen companion star. The truth is, we still don't fully understand what's happening with Betelgeuse, but one thing's for sure, this star isn't just a fading giant. It's a cosmic enigma, challenging everything we thought we knew about how stars behave in their final years. And as it keeps sending us these strange, flickering signals, one question lingers: what will it do next? But the surprises from Betelgeuse don't stop there. Just when astronomers thought they'd seen it all, this red giant threw another curveball, massive, unpredictable flares erupting from its surface. Unlike the steady pulses we see from most aging stars, Betelgeuse's flares burst forth without warning, like solar storms on steroids. These aren't just minor flickers. Some of these eruptions shoot material far into space at speeds that defy our current models of stellar behavior. Recent observations have caught Betelgeuse in the act, with telescopes recording violent ejections of plasma that stretch millions of miles into the surrounding cosmos. What's truly baffling is that these flares don't match any known pattern. Most stars, even unstable ones, follow some kind of rhythm, but Betelgeuse seems to operate on pure chaos. Some researchers suggest these outbursts could be tied to massive bubbles of hot gas rising from deep within the star, while others wonder if magnetic fields near the surface are twisting and snapping, releasing energy in sudden, explosive bursts. The implications are huge. If Betelgeuse's flares are rewriting the rules of how red giants behave, it could force us to rethink stellar evolution entirely. Stars like this are supposed to fade quietly, but Betelgeuse is doing anything but. Every flare, every dimming event is another piece of a puzzle we're still trying to solve. And with each new observation, one thing becomes clearer. This star isn't just a relic of the cosmos. It's a living laboratory, showing us just how much we still have to learn about the final stages of a star's life. So what's next for Betelgeuse? Will it keep surprising us with more violent outbursts, or is this just the prelude to something even bigger? Only time and a lot more observation will tell. But for now, this fiery giant remains one of space's most captivating mysteries. Now, shifting our gaze from the fiery chaos of Betelgeuse, let's turn toward Orion, where another red giant is stirring up intrigue with something far more subtle, yet equally puzzling. Deep within this constellation lies a star emitting faint, rhythmic signals that sound almost deliberate, like whispers in the dark. Unlike the violent flares we've seen elsewhere, this signal repeats with eerie precision, mimicking patterns that at first glance seem anything but natural. What makes these whispers so unsettling is their structure. Most stellar signals are messy, shaped by turbulence and random energy bursts, but this one, it's clean, repetitive, almost like a heartbeat. Astronomers first dismissed it as interference, maybe even a glitch in their instruments. But as the pattern persisted across multiple observations, the debate heated up. Could this be some bizarre stellar quirk, or are we picking up something far more extraordinary, a signal with purpose? The natural explanations are just as fascinating as the extraterrestrial ones. Some theorists argue it could be caused by shock waves rippling through the star's outer layers, creating a feedback loop that amplifies certain frequencies. Others point to hypothetical planets or debris disks interacting with the star's magnetic field in ways we've never seen. But then there's the wild card, the possibility of artificial origin. The signal's regularity has drawn comparisons to early SETI detections, sparking cautious excitement. Could this be a cosmic beacon, or are we simply seeing nature's version of a broken record? For now, the mystery endures. Without clearer data or a smoking gun explanation, the whispering giant remains a tantalizing enigma, one that challenges our assumptions about what red giants can do. Whether it's a natural phenomenon pushing the boundaries of physics or something even more profound, this star reminds us that the universe still holds secrets we're only beginning to uncover. And as long as those whispers keep coming, astronomers will keep listening. Now, let's journey from the enigmatic whispers of Orion to the haunting echoes of Antares, a red giant that's rewriting the rules of stellar communication. Unlike the steady rhythms we've encountered so far, Antares sends its signals in strange, delayed bursts, like a cosmic message that arrives in fragments, defying everything we thought we knew about how stars behave. What's baffling astronomers isn't just the delay, but the way these signals seem to stagger. Normally, energy from a star's surface radiates outward in a predictable flow. But Antares, its signals hiccup. They arrive in clusters, sometimes seconds apart, sometimes minutes, as if something invisible is bending or blocking their path. The leading theory points to its atmosphere, a turbulent, superheated blanket of gas that might be acting like a funhouse mirror, distorting and scattering light in ways we've never observed before. This isn't just a curiosity, it's a challenge to our textbooks. Red giants were thought to have relatively stable outer layers, but Antares suggests otherwise. Its ghostly echoes hint at pockets of extreme density or magnetic knots that trap and release energy at random. Some researchers even speculate about unseen structures, like vast plasma waves or debris clouds, twisting the signals before they reach us. The implications are profound. If Antares isn't alone in this behavior, we might need to rethink how we model aging stars altogether. Are these echoes a quirk of Antares or a hidden feature of red giants we've overlooked? For now, the star keeps its secrets, sending bursts that taunt us with questions. And with every flicker, it reminds us the universe's playlist is far stranger than we imagined. But just as Antares leaves us with more questions than answers, another red giant steps into the cosmic spotlight, Mu Cephei, a star that doesn't just flicker or hiccup but sings. Imagine tuning into the universe's radio and stumbling upon a melody, a rhythmic pulse so precise it feels almost composed. That's what astronomers detected from Mu Cephei harmonic vibrations, a series of frequencies so orderly they defy the chaotic nature of dying stars. At first glance, these vibrations might seem like natural resonances, the kind you'd expect from a massive, turbulent star. Mu Cephei's outer layers churn with convection, and like a colossal bell, those movements could generate rhythmic waves. But here's the twist. The patterns are too clean, too repetitive. Natural stellar resonances usually come with noise, slight variations caused by the star's internal chaos. Mu Cephei's signals, though, they're eerily consistent, almost as if something or someone is fine-tuning them. Of course, the scientific community is divided. One camp argues these harmonics are a product of sheer scale. Mu Cephei is one of the largest known red giants, and its sheer size might amplify certain vibrations into detectable musical patterns. Others point to magnetic fields, suggesting they could act like cosmic strings, plucking the star's atmosphere into rhythmic pulses. But then there's the fringe theory, the one that raises eyebrows. Could these frequencies be a form of communication, a stellar beacon intentionally structured? Before we leap to extraterrestrial conclusions, let's ground ourselves in what we know. Mu Cephei's vibrations, however strange, offer a rare window into stellar mechanics. If they're natural, they could teach us how energy travels through these aging giants. If there's something else, well, that's a mystery worth listening to. For now, the star keeps humming its cosmic tune, and whether it's a lullaby or a siren's call, one thing's certain: the universe just got a little more musical. Now, let's turn our attention from the musical hum of Mu Cephei to something far more jarring: the silent scream of Canis Majoris. This red hypergiant, one of the largest stars known to humanity, stunned astronomers when it unleashed a sudden, violent burst of energy, only for it to vanish without a trace moments later. Picture this: a star so massive it could swallow our entire solar system, suddenly flaring up with the intensity of a cosmic explosion, then falling eerily silent as if nothing happened. What makes this event so baffling is its sheer abruptness. Most stellar outbursts, like supernova or solar flares, leave behind clues: expanding shockwaves, lingering radiation, or debris. But why Canis Majoris' scream left no trace? One theory suggests it could have been a failed supernova, a collapse that somehow stalled mid-explosion, leaving the star intact but briefly convulsing. Another idea points to magnetic reconnection, where tangled magnetic fields snap and release colossal energy like a rubber band stretched too far. Then there's the wild card: external interference. Could something have passed between us and the star, briefly magnifying its light? Or was the burst not from the star itself, but from an unseen object nearby, a black hole or neutron star interacting with it? The lack of residual evidence makes this a cosmic whodunit. For now, why Canis Majoris looms quietly in the sky, its silent scream a reminder that even the mightiest stars can harbor secrets we're only beginning to unravel. Whether it was a stellar hiccup or something far stranger, one thing's clear: the universe still has a few tricks up its sleeve. Moving from the enigmatic silence of Canis Majoris, let's shift our gaze to a star that refuses to stay still: Aldebaran, the fiery eye of Taurus. Unlike the steady glow we expect from red giants, Aldebaran behaves more like a flickering candle in the cosmic wind, its brightness dancing between extremes without any clear rhythm. This erratic flickering has left astronomers scratching their heads. Normally, stars like Aldebaran pulse in predictable cycles, expanding and contracting as they age. But Aldebaran's light dips and surges at random, almost as if something unseen is tugging at it. One leading theory: a hidden companion, perhaps a dim star, a rogue planet, or even a dense, dark object like a brown dwarf, could be orbiting close enough to disturb Aldebaran's stability. Imagine a dancer twirling gracefully, only to be yanked off balance by an invisible partner. That's the kind of gravitational interference scientists suspect might be at play here. If such a companion exists, its gravity could warp Aldebaran's outer layers, causing those strange, unpredictable brightening and dimming episodes. But here's the twist: despite years of searching, no companion has been definitively spotted. Telescopes have scoured the space around Aldebaran, yet the culprit remains elusive. Some argue the flickering could stem from turbulent magnetic activity within the star itself, while others wonder if interstellar dust clouds might be filtering its light in odd ways. Whatever the cause, Aldebaran's flickering serves as a humbling reminder that even the brightest stars in our sky can hide mysteries in their shadows. And until we unravel this puzzle, its unpredictable glow will keep us guessing. Now, let's dig deeper into the mystery of Aldebaran's hidden companion. The idea of an unseen object tugging at this red giant isn't just speculation, it's grounded in some compelling evidence. For starters, astronomers have noticed subtle wobbles in Aldebaran's motion, the kind that often betray the presence of an orbiting partner. These tiny gravitational tugs suggest something massive, yet invisible, might be lurking nearby. One leading candidate is a brown dwarf, a failed star too small to ignite nuclear fusion but large enough to exert a strong gravitational pull. If one were circling Aldebaran, it could easily explain the erratic flickering. Another possibility is a dense, dim star, like a white dwarf, whose faint glow might be lost in Aldebaran's brilliance. Even a massive planet, many times heavier than Jupiter, could be the culprit, warping the star's outer layers as it orbits, but not everyone is convinced. Skeptics point out that despite advanced telescopes and years of observation, no direct trace of a companion has been found. Some researchers argue that Aldebaran's flickering could stem from internal chaos, violent magnetic storms, or turbulent convection in its outer layers. Others suggest passing interstellar dust clouds might be distorting our view, creating the illusion of irregular brightness. The debate highlights a fascinating challenge in astronomy. Sometimes the absence of evidence is just as puzzling as the evidence itself. Until we catch a definitive glimpse of this hypothetical companion, or rule it out entirely, Aldebaran's flickering will remain one of the sky's most tantalizing unsolved puzzles. And that's what makes it so thrilling. The hunt for answers is far from over. Now, shifting our gaze to the constellation Cetus, we encounter Mira, a red giant that's been baffling astronomers with its rhythmic, almost musical signals. Unlike the chaotic flickering of Aldebaran, Mira's emissions follow a precise, repeating pattern, like a cosmic metronome ticking across the void. At first glance, this regularity might seem like a natural pulsation, the kind common in variable stars. But there's a twist. The intervals and intensities of these pulses aren't just random fluctuations, they align in a sequence so consistent, it almost feels deliberate. One school of thought suggests this could be a phenomenon known as stellar seismology, where internal pressure waves ripple through the star's layers, creating predictable vibrations. Imagine a bell ringing in space, each note echoing the star's internal structure. Yet others find the patterns too intricate to dismiss as mere echoes of stellar mechanics. The pulses occasionally shift in ways that defy conventional models, sparking whispers of something more enigmatic. Could we be detecting the fingerprints of an advanced civilization modulating the star's light? It's a tantalizing idea, though skeptics are quick to point out that nature often crafts patterns far stranger than fiction. The debate hinges on a critical question: where do we draw the line between natural complexity and potential artifice? For now, Mira's code remains unbroken, a celestial cipher waiting for its key. Whether it's the heartbeat of a dying star or a message in the dark, one thing's certain: the universe loves a good mystery. And as we'll see next, some signals don't just repeat, they vanish without a trace. Now, let's turn our attention to Epsilon Pegasi, a red giant that's playing a cosmic game of hide and seek with astronomers. Unlike Mira's rhythmic pulses, the signals from Epsilon Pegasi are downright ghostly, appearing without warning, then vanishing just as quickly, leaving no trace behind. One moment, telescopes pick up a clear, strong emission, and the next it's gone, as if the star decided to flicker out of existence. At first, scientists wondered if this was just a glitch, a hiccup in the instruments or interference from Earth's atmosphere. But here's the catch: the same phantom pulses have been detected by multiple observatories, ruling out simple technical errors. That's when things got interesting. Could it be something blocking the signal, like a dense cloud of dust or a rogue planet passing in front of the star? Or is Epsilon Pegasi itself undergoing bizarre, short-lived eruptions that defy our current understanding of stellar behavior? The mystery deepens when you consider the timing. These pulses don't follow any predictable schedule. They're random, sporadic, and frustratingly elusive. Some researchers speculate they might be tied to magnetic storms or turbulent plasma surges deep within the star, while others entertain the wilder idea of transient cosmic phenomena we've yet to discover. Whatever the cause, Epsilon Pegasi's phantom pulses remind us that even the most advanced telescopes can't always decode the universe's quirks. And just when you think you've seen it all, space throws another curveball, like the next signal we're about to uncover, where time itself seems to bend around a distant red giant. Now, shifting our gaze deeper into the cosmos, we encounter Gamma Crucis, a red giant that seems to toy with the very fabric of time. Unlike the phantom pulses of Epsilon Pegasi, the signals from Gamma Crucis arrive with bizarre, inconsistent delays, as if they're stumbling through an invisible obstacle course. Imagine shouting into a canyon and hearing your echo return seconds later, then minutes later, with no rhyme or reason. That's the kind of puzzle astronomers face here. At first glance, you might blame interstellar gas or dust, the usual suspects for slowing down light. But the delays from Gamma Crucis don't match the known distribution of these materials in space. Some signals lag by mere hours, others by days, defying the predictable slowdown we'd expect. This has led scientists to wonder, could there be pockets of unseen matter warping the signals like cosmic potholes in the interstellar highway? Or perhaps something even stranger, like rogue gravitational waves or distortions in spacetime itself. The implications are staggering. If the interstellar medium isn't as uniform as we thought, it could rewrite how we map the galaxy's structure. Some theorists even suggest these delays might reveal hidden dark matter clumps, invisible except for their ghostly drag on passing light. Others propose turbulent magnetic fields, twisting and delaying signals like a funhouse mirror. Whatever the cause, Gamma Crucis forces us to confront a humbling truth. Space isn't just empty void. It's a dynamic, messy frontier, and every unexplained delay might be a clue to something extraordinary lurking in the shadows. And just when you think the universe can't get any weirder, our next signal takes the mystery even further, into the heart of a binary system where two stars defy all expectations. Now, let's turn our attention to a cosmic duo that's rewriting the rules of stellar partnerships, Alpha Hercules. This binary system, where two red giants orbit each other, should be a harmonious dance of predictable signals. But instead, it's more like a pair of musicians playing entirely different tunes. One star pulses with steady rhythm, while the other erupts in chaotic bursts, as if they're not even part of the same system. What makes this so baffling is that binary stars are supposed to influence each other. Their gravitational pull should synchronize their behavior like twins sharing a heartbeat. Yet here, one star seems utterly indifferent to its partner's presence. Astronomers have scrambled to explain this disconnect. Could one star be older, its internal structure fraying in ways that disrupt the usual binary dynamics? Or is there an unseen third object, a stealthy black hole or neutron star, throwing the system into chaos? The implications ripple far beyond Alpha Hercules. If binary stars don't always play by the rules, it challenges decades of assumptions about how these systems evolve. Some theories suggest magnetic fields or turbulent stellar winds might be to blame, creating invisible barriers between the stars. Others wonder if we're witnessing a rare snapshot of a system mid-collapse, where one star is on the verge of engulfing the other. Whatever the answer, Alpha Herculis forces us to rethink how stars interact and reminds us that even in the vastness of space, relationships can be messy. And just when we think we've seen it all, the cosmos delivers another curveball, a signal so strange it resembles a call for help. Now, shifting our gaze to Delta Andromedae, we encounter a signal that sends chills down the spine, a pattern so eerily structured it mimics a cosmic cry for help. Unlike the chaotic bursts of Alpha Herculis, this red giant emits pulses in a rhythmic sequence, almost like Morse code. The regularity is uncanny, with intervals so precise they defy typical stellar behavior. It's as if the star is tapping out a message across the void. Scientists first dismissed it as a quirk of stellar pulsations, but the more they studied it, the harder it became to ignore the parallels with artificial signals. The pattern repeats every 11 hours, a cadence that doesn't align with known natural processes in red giants. This anomaly sparked fierce debate. Could it be the result of some exotic stellar physics, like shockwaves reverberating through the star's atmosphere? Or are we picking up something far more extraordinary, a deliberate transmission? The SETI community took immediate notice, while most researchers urge caution, pointing to Earth's history of misinterpreting natural phenomena as signs of intelligence. Others argue this signal warrants serious scrutiny. After all, red giants aren't known for producing such orderly patterns. Could it be a beacon from an advanced civilization, or perhaps a malfunctioning relic of alien technology? Skeptics counter that interstellar plasma or magnetic fields might sculpt the signal into its strange shape. What makes Delta Andromeda's signal so gripping is the tension between possibility and skepticism. It's a reminder that the line between natural wonder and potential contact is razor thin. And as telescopes grow more sensitive, the question lingers: are we listening to a dying star's final act or something far more profound? Up next, another red giant defies expectations, this time with a heartbeat so erratic it leaves astronomers scrambling for answers. Now, let's turn our attention to Zeta Aurigui, a red giant that doesn't just pulse, it stutters. Unlike the rhythmic signals we've seen so far, this star's heartbeat is wildly unpredictable, skipping beats and surging without warning. Astronomers expected the steady, predictable pulsations typical of red giants, but Zeta Aurigui throws that rulebook out the window. Its light flickers and flares in a chaotic dance, defying every model of stellar behavior. What could be causing this cosmic arrhythmia? One leading theory points to turbulence deep within the star itself. Red giants are massive, with churning layers of gas and plasma, and Zeta Aurigui might be experiencing violent internal disruptions, like a pot of boiling water with no lid. Magnetic fields could be twisting and snapping, or convection currents might be clashing in ways we don't yet understand. Some researchers even speculate that the star's core is undergoing strange, unstable reactions, sending shockwaves rippling outward. But here's the twist: Zeta Aurigui isn't alone in its odd behavior. A handful of other red giants show similar irregularities, hinting that this might be a rare but natural phase in stellar evolution. The challenge is figuring out why. Is it a sign of the star's impending death throes, or just a temporary tantrum? Telescopes are now trained on Zeta Aurigui, watching for clues in its flickering light. Every erratic pulse could be a piece of the puzzle, one that might rewrite how we understand the final chapters of a star's life. Up next, we'll dig even deeper into Zeta Aurigui's turmoil, exploring how its internal chaos could reshape our ideas about stellar magnetism and structure. The mystery is far from solved, but one thing's clear: this star refuses to play by the rules. Now, let's peel back the layers of Zeta Aurigui's chaos to uncover what's really happening beneath its fiery surface. The star's erratic signals aren't just random noise, they're clues pointing to a storm of activity deep within. One of the most compelling explanations revolves around its magnetic fields. Imagine a colossal, invisible web of magnetic lines wrapping around the star, constantly stretching and snapping. When these fields suddenly reorganize, they can unleash bursts of energy like cosmic lightning strikes, disrupting the star's steady glow. Some astronomers believe Zeta Aurigae's magnetic fields might be tangled beyond recognition, creating pockets of instability that trigger those unpredictable flares. But magnetism isn't the only suspect. Convection, the process that moves heat from the star's core to its outer layers, could also be playing a role. In a normal red giant, convection currents rise and fall in a predictable rhythm like waves in an ocean. But Zeta Aurigae's currents might be crashing into each other, creating turbulent eddies that distort its light output. Picture a pot of water boiling over, except here, the water is superheated plasma, and the pot is a star thousands of times larger than our Sun. These convective anomalies could be stirring up chaos, making the star's pulses stagger and stumble. What makes this even more intriguing is the possibility that these two forces, magnetism and convection, are working together in ways we've never seen. Magnetic fields might be guiding the convection currents or vice versa, amplifying the star's irregularities. It's a cosmic feedback loop, and Zeta Aurigae is the laboratory. Recent observations suggest that when the star's magnetic activity spikes, its convective zones become even more unruly, as if they're feeding off each other's energy. The big question now is whether this turmoil is a fleeting phase or a sign of something more dramatic. Could Zeta Aurigae be on the verge of a massive eruption, or is this just how some red giants behave as they age? Every flicker, every surge brings us closer to an answer, and closer to rewriting the textbook on how stars like this live, thrash, and eventually fade away. Up next, we'll turn our gaze to another cosmic rebel, Lambda Velorum, a red giant that didn't just flicker, it vanished entirely. Where did it go and why? The mystery deepens. Now, let's shift our focus to one of the most baffling disappearances in the cosmos, Lambda Velorum. This red giant didn't just flicker or act erratically, it vanished completely, leaving astronomers staring at empty data for years. Then, just as mysteriously, its signals returned, as if the star had stepped back into the spotlight after an unexplained hiatus. What could cause a star to go silent like this, and what does it tell us about the hidden lives of red giants? One leading theory points to dust clouds, thick cosmic veils that might have drifted between Lambda Velorum and Earth. Picture a fog so dense it blots out a lighthouse's beam. If enough dust accumulated around the star or along our line of sight, it could temporarily obscure its light, making it seem like the star had disappeared. Over time, as the dust dispersed or moved on, the star's signals would reappear. But here's the catch: dust clouds usually don't vanish so cleanly. They tend to leave traces, subtle changes in the star's color or infrared signatures. Lambda Velorum's return was eerily crisp, with no lingering haze, leaving some scientists skeptical of this explanation. Another possibility is that the star itself underwent a dramatic but invisible transformation. Red giants are known for their cycles of activity, much like the Sun's quieter and stormier phases, just on a far grander scale. If Lambda Velorum entered an unusually calm period, its outer layers might have contracted slightly, reducing its brightness below our detection threshold. Then, as activity ramped back up, the star's glow returned to normal. But this raises a question: why would a star's dimming be so sudden and total? Most stellar cycles are gradual, not like flipping a switch. Then there's the wildcard theory, something far more speculative but thrilling to consider. Could Lambda Velorum have ejected a massive shell of material, a kind of stellar burp, that briefly enveloped it? Such events are rare but not unheard of in aging stars. If the ejected material cooled quickly, it might have formed a temporary shroud around the star, blocking its light until the shell expanded and thinned out. Observations of similar stars hint at this possibility, but Lambda Velorum's case remains unique in its abruptness. The mystery deepens when we consider that Lambda Velorum isn't the only red giant to pull this vanishing act. A handful of others have done the same, suggesting this might be a rare but natural phase in some stars' lives. Yet each time it happens, it challenges our assumptions about how stars behave in their final years. Is this a preview of a coming explosion, a sign of internal upheaval, or just a cosmic sleight of hand we don't yet understand? As we piece together the clues, one thing is clear. Lambda Velorum's disappearing act is more than a curiosity. It's a puzzle that could rewrite how we think about stellar aging. Up next, we'll examine another enigma, Omicron Ceti, a star that doesn't just send signals but seems to throw them back at us like a cosmic echo. What's behind this mirror effect, and could it reveal secrets about the space between the stars? Now, let's turn our attention to a signal that plays tricks with time, Omicron Ceti, the star that seems to talk back. Unlike Lambda Velorum's vanishing act, Omicron Ceti does something even stranger. It sends signals that bounce back to us like a cosmic echo. Imagine shouting into a canyon and hearing your voice return seconds later, except here, the canyon is deep space and the echo comes from a star. What could possibly explain this mirror effect? One straightforward answer lies in the concept of light echoes. When a star emits a burst of light, that light can reflect off nearby clouds of dust or gas, creating a delayed echo that reaches us later. It's like a flashlight beam hitting a mirror in a dark room. The reflection arrives just a moment after the original. In Omicron Ceti's case, astronomers have detected signals that match this pattern, suggesting there might be a dense shell of material around the star, bouncing its light back to us. Observations of similar stars support this idea, with some even showing multiple echoes as light ricochets through complex dust structures. But here's where it gets weird. Some of Omicron Ceti's reflected signals don't behave like typical light echoes. Instead of fading predictably, they sometimes intensify or shift in wavelength, as if something out there is altering the signal before sending it back. Could this be more than just passive reflection? One hypothesis suggests that magnetic fields or plasma waves in the surrounding environment might be reshaping the signals, turning them into something new by the time we detect them. It's a bit like shouting into that canyon and hearing your words come back rearranged, unnerving, and hinting at forces we don't fully understand. Then there's the fringe theory, admittedly speculative but fascinating, that Omicron Ceti's echoes aren't natural at all. Could we be looking at some form of intentional signal manipulation? Before you jump to extraterrestrial conclusions, consider this. Advanced civilizations, if they exist, might use stellar environments as cosmic amplifiers or relays. While there's zero concrete evidence for this, the idea sparks debate about how we interpret anomalies in the first place. After all, science often starts with what if. Before narrowing down to here's why, what makes Omicron Ceti particularly intriguing is how it challenges our assumptions about communication or miscommunication across space. Light echoes are a known phenomenon, but when they defy expectations, they force us to rethink the environments around these aging stars. Are we seeing the aftermath of a stellar eruption, the ripple effects of a hidden companion, or something entirely unexpected? Each echo carries clues, and astronomers are listening closely. Up next, we'll confront a star that defies the rules of temperature Sigma Octantis, where the heat doesn't behave the way it should. How can a red giant's signals point to both scorching and freezing conditions at once? The answer might rewrite what we know about stellar atmospheres. Now, let's tackle a star that seems to have a serious identity crisis, Sigma Octantis, where the temperature readings make no sense at all. Normally, red giants follow predictable patterns when it comes to heat, but Sigma Octantis flips the script entirely. One moment, its signals scream scorching hot, and the next they plunge into freezing territory, as if the star can't decide what it wants to be. This isn't just a minor glitch, it's a full-blown contradiction of everything we know about stellar behavior. Standard models tell us that red giants should have relatively stable outer layers, with temperatures that change gradually over time. But Sigma Octantis behaves more like a malfunctioning thermostat, swinging between extremes faster than astronomers can explain. Some theories suggest violent magnetic activity deep within the star could be responsible, twisting and churning its atmosphere in ways we've never seen before. Imagine a pot of water boiling furiously 1 second, then turning to ice the next. That's the level of chaos we're dealing with here. Another possibility points to hidden companions or debris disks interacting with the star in unexpected ways. If a nearby object, like a rogue planet or dense cloud of material, were periodically blocking or reflecting Sigma Octantis' light, it might create the illusion of wild temperature swings. But here's the catch: no such object has been detected, leaving this idea in the realm of speculation. What really stumps scientists is how these fluctuations don't align with the star's other behaviors. Its brightness and size remain steady, which makes the temperature spikes and drops even more baffling. It's like someone turning the oven dial randomly while the cake inside stays perfectly baked. Could there be unknown processes happening in the star's outer layers, something our current models just can't account for? One bold hypothesis even suggests that Sigma Octantis might be a rare hybrid, a red giant with remnants of a white dwarf's behavior lurking beneath the surface. If true, this could rewrite parts of stellar evolution theory, proving that stars don't always follow the rules we've written for them. As we move forward, keep this question in mind: what happens when a star's gravity seems to bend the rules? Next up, we'll explore Theta Persei, where the signals hint at gravitational ripples that shouldn't exist. What's warping space around this red giant, and could it be something science has yet to name? Now, let's shift our gaze to Theta Persei, a red giant that's bending the rules of gravity itself. Astronomers have detected strange ripples in its signals, tiny distortions that shouldn't exist if this star were playing by the usual cosmic rulebook. These gravity-like waves hint at something massive lurking nearby, something we can't yet see. Theta Persei's signals flicker with a rhythmic wobble, as if an invisible hand is tugging at the star. Normally, red giants don't produce gravitational waves. Those are the domain of colliding black holes or neutron stars. Yet here we are, staring at a star that seems to be doing just that. One theory suggests an unseen companion, like a black hole or a neutron star, might be orbiting Theta Persei, warping space-time around it. But here's the twist: telescopes haven't spotted anything nearby. Another possibility dives into exotic physics. Could Theta Persei be interacting with dark matter in a way we've never observed? Or is there some bizarre stellar phenomenon at work, like a magnetic field so intense it mimics gravity waves? The data doesn't fit neatly into any existing box, leaving scientists scratching their heads. What makes this even stranger is how consistent these ripples are. Unlike the chaotic temperature swings of Sigma Octantis, Theta Persei's distortions follow a clear pattern, almost like a heartbeat. That regularity suggests something deliberate, a cosmic dance we don't yet understand. As we piece together the puzzle, one question lingers: are we witnessing the fingerprints of an undiscovered object, or is Theta Persei revealing a flaw in our understanding of gravity itself? Next up, we'll unravel the chromatic mysteries of Iota Draconis, where light itself seems to shift in ways that defy explanation. Now, let's turn our attention to Iota Draconis, where the light itself seems to be playing tricks on us. This red giant isn't just flickering or pulsing, it's shifting its colors in ways that leave astronomers baffled. Imagine watching a star change its hue like a cosmic chameleon, with no clear reason why. What makes Iota Draconis so puzzling is the unpredictability of these chromatic shifts. One moment, its light leans heavily toward the red end of the spectrum, and the next, it's skewing blue or even violet. These aren't subtle changes, they're dramatic swings that defy the steady behavior we expect from stars of its kind. one leading theory points to turbulent atmospheric disturbances. Red giants have massive, churning outer layers, and if pockets of gas or dust erupt unevenly, they could scatter light in strange ways. Think of it like sunlight filtering through a stormy sky, except here, the storm is happening on a stellar scale. But there's another contender: magnetic fields. Iota Draconis might harbor magnetic activity far more intense than we've seen in other red giants. If these fields twist and snap, they could warp the star's light, bending it into unexpected colors. It's like holding a prism in a hurricane utter chaos with flashes of bizarre beauty. The real mystery: these shifts don't follow any obvious pattern. Unlike Theta Persei's rhythmic gravity ripples, Iota Draconis's color changes seem almost random. That inconsistency has some researchers wondering if we're missing a piece of the puzzle, something hidden beneath the surface or even beyond our current physics. Could there be an unseen companion influencing the star's light? Or is Iota Draconis revealing a new kind of stellar behavior we've never catalogued before? As we dig deeper, one thing's certain: this star refuses to fit into any neat cosmic box. Up next, we'll explore how magnetic fields might be the key to unlocking Iota Draconis's secrets, or if they're just another red herring in this stellar enigma. Now, let's pull back the curtain on Iota Draconis's magnetic mysteries. Recent observations suggest this star's magnetic fields might be more chaotic than we ever imagined. While most red giants have relatively stable magnetic activity, Iota Draconis behaves like a cosmic rebel, with fields that twist, snap, and realign in ways that could explain its erratic color shifts. A study published just last year used advanced spectropolarimetry, a way to measure magnetic fields by studying polarized light, and found something startling. Iota Draconis's magnetic fields aren't just strong, they're tangled like a ball of yarn after a cat's play session. These knots could distort the star's light as it escapes, bending different wavelengths unevenly and creating those bizarre color changes. But here's the twist: not all the data fits. Some color shifts happen too fast for magnetic fields alone to explain. That's led researchers to wonder if something else is at play. Perhaps interactions with an unseen companion, or even exotic physics we haven't discovered yet. One team proposed that magnetic reconnection events, sudden releases of energy when field lines break and reconnect, might be supercharging the shifts, but even that doesn't account for every observation. The biggest unanswered question: why Iota Draconis alone seems to have this level of magnetic chaos. Other red giants with similar sizes and ages don't show anything close to this behavior. Is it a rare phase in a star's life, or is there something uniquely unstable about this particular giant? As we piece together the clues, one thing's clear: Iota Draconis isn't just a puzzle, it's a challenge to our understanding of how stars age and evolve. Up next, we'll turn our attention to another cosmic head-scratcher, the phantom companion of Kappa Geminorum, where the signals hint at an invisible dance partner no telescope can see. Now, let's shift our gaze to Kappa Geminorum, where the signals tell a story of something lurking in the shadows, something we can't quite see. This red giant has been sending out strange wobbles in its light, the kind that usually betray the presence of a nearby companion. But here's the catch: no matter how hard astronomers look, they can't spot anything orbiting it. So what's tugging on Kappa Geminorum? One leading theory points to a black hole, a dark, dense remnant of a collapsed star, invisible to telescopes but still exerting a gravitational pull. If true, this would be a rare find, as black holes orbiting red giants aren't exactly common. Another possibility is a neutron star, the ultra-dense core left behind after a supernova. These objects are tiny but pack enough gravity to yank on their stellar neighbors. Then there's the skeptic's take: maybe it's not a hidden object at all. Could these signals just be glitches in the data, or perhaps quirks in Kappa Geminorum's own behavior? Some researchers argue that unusual stellar activity, like massive magnetic flares or internal turbulence, might mimic the effects of an unseen companion. But the plot thickens when you look at the timing. The wobbles follow a pattern, repeating at regular intervals exactly what you'd expect if an invisible object were circling the star. That consistency makes it hard to dismiss as mere noise. The mystery of Kappa Geminorum forces us to ask, are we seeing the footprint of something truly exotic, or is this a cosmic illusion? Up next, we'll explore another synchronized enigma, the strange, pulsing harmony of Nu Ophiuchi, where multiple red giants seem to be singing in unison. Now, let's turn our attention to Nu Ophiuchi, where something truly bizarre is unfolding. Imagine a cosmic choir, multiple red giants pulsing in perfect sync, as if following an unseen conductor. This isn't just a coincidence. These stars scattered across space are emitting signals that align with eerie precision. So, what could be behind this strange harmony? One explanation leans on natural resonance, a phenomenon where stars vibrate at matching frequencies due to similar internal structures or ages. Think of it like tuning forks humming the same note when struck. If these red giants share certain properties, their pulsations might naturally fall into step. But there's a twist. The synchronization is so exact that some researchers wonder if something external is pulling the strings. Could an unseen force like a dense object or a ripple in space-time be orchestrating this stellar symphony? It's a wild idea, but not impossible. Gravitational waves or even a hidden black hole might be nudging these stars into alignment. Then there's the skeptic's view. Could this just be a trick of timing, a fleeting moment where random pulses happen to overlap? The odds are slim, but not zero. Yet, the longer astronomers observe, the more the pattern holds, making randomness harder to swallow. Nu Ophiuchi's synchronized dance leaves us with a tantalizing question. Is this the universe's way of showing us a new kind of stellar behavior, or is there an invisible hand at work? Up next, we'll unravel the whispered echoes of Pi Hydrae, where faint signals seem to repeat like a cosmic game of telephone. Now, shifting our gaze to Pi Hydrae, we encounter a mystery that feels almost like the universe is whispering back at us. This red giant emits faint signals that don't just fade away, they bounce back, repeating like echoes in a cosmic canyon. At first glance, this seems like a classic case of a light echo, where light from the star reflects off nearby dust or gas, creating a delayed copy of the original signal. It's like shouting into a valley and hearing your voice return moments later. But here's where things get intriguing. The echoes from Pi Hydrae aren't just random reverberations. They follow a pattern that's a little too precise, almost as if they're being deliberately repeated. Some astronomers argue this could still be explained by complex structures in the surrounding interstellar medium, maybe a dense cloud or a shell of material left behind by the star itself. Yet others can't shake the feeling that there's more to it. Could these echoes be the result of something we haven't yet imagined, like an unknown stellar process or even an interaction with an unseen object? Then there's the timing. The delays between the original signal and its echoes don't always match what we'd expect from simple reflections. It's as if the universe is playing a game of telephone, but the message comes back slightly altered. This has led to wilder theories, like the possibility of space-time itself warping the signals in ways we don't fully understand. So, is Pi Hydrae just showing us a quirky twist on a known phenomenon, or is it hinting at something entirely new? The answer might lie in the next signal. We explore the quantum glitch of Tau Ceti, where the rules of physics seem to bend in unexpected ways. Now, let's turn our attention to Tau Ceti, where the signals we're picking up aren't just puzzling, they're downright bizarre. This red giant is emitting something that looks eerily like quantum noise, the kind of random flickering you'd expect at the subatomic level, not from a massive star light years away. At first, researchers brushed it off as a glitch in the instruments, maybe interference from Earth's atmosphere or a hiccup in the data processing. But the more they looked, the harder it became to ignore. The patterns in these signals don't match any known source of noise, and that's where the real mystery begins. One camp of scientists insists this has to be a technical artifact. After all, space is full of cosmic static, and our telescopes aren't perfect. They argue that what we're seeing is just the limits of our technology, not some revolutionary discovery. But others aren't so sure. They point out that the noise from Tau Ceti has a strange coherence to it, almost as if it's following rules we haven't figured out yet. Could this be a hint of quantum effects playing out on a stellar scale? Imagine the implications if true, a star behaving like a particle in a lab experiment, blurring the line between the tiny and the cosmic. Then there's the timing. These glitches don't happen randomly. They cluster in ways that defy simple statistical chance, almost like the star is switching between different states. Some theorists have even floated the idea of exotic physics, like quantum entanglement spanning astronomical distances or hidden dimensions influencing the star's behavior. It sounds like science fiction, but when the data keeps surprising you, sometimes the wildest ideas deserve a second look. So, is Tau Ceti revealing a flaw in our instruments, or is it offering us a front-row seat to physics we've never seen before? The debate is far from settled, but one thing's clear: this star isn't playing by the usual rules, and that makes it the perfect lead into our next signal, where the chaos of Upsilon Scorpii takes center stage. Now, shifting our gaze to Upsilon Scorpii, we encounter a cosmic symphony gone wrong. This red giant isn't just sending out signals, it's broadcasting chaos. Unlike the steady pulses we expect from stars of its size, Upsilon Scorpii's emissions clash and collide, creating a dissonant pattern that's left astronomers scratching their heads. Imagine tuning into a radio station and hearing a dozen songs playing at once, each fighting for dominance. That's the kind of chaotic noise we're dealing with here. At first glance, this mess of signals might seem like random interference, but there's a method to the madness. Researchers have noticed something peculiar: the chaos isn't entirely random. Buried in the noise are faint echoes of order, like fragments of a shattered melody. Some scientists believe this could be the aftermath of a violent stellar collision or a merger with another massive object. Picture two stars spiraling into each other, their signals tangling into a cosmic knot that lingers long after the event. Others argue it might be something even more exotic. Could Upsilon Scorpii be harboring a hidden companion, like a black hole or neutron star, whose gravitational pull is warping its emissions? The star's erratic behavior could be the result of intense tidal forces, stretching and twisting its signals into that bizarre clashing pattern. Or perhaps we're seeing the birth pangs of a new phenomenon, a star undergoing internal upheavals so extreme they disrupt its very heartbeat. Whatever the cause, one thing's certain: Upsilon Scorpii refuses to conform. Its dissonant harmony challenges our understanding of how stars communicate, leaving us with more questions than answers. And as we move forward, this chaos sets the stage for an even deeper mystery: the sudden silence of Rho Cassiopeiae, a giant that chose to stop speaking altogether. Now, let's turn our attention to a mystery that's as unsettling as it is fascinating: the sudden silence of Rho Cassiopeiae. This red giant was once a reliable beacon in the cosmos, emitting steady signals for decades, until one day, without warning, it simply stopped. Imagine a friend who's always been chatty suddenly going mute, leaving you wondering what happened. That's the kind of eerie quiet we're dealing with here. At first, astronomers thought it might be a technical glitch, a problem with the telescopes or instruments. But when the silence persisted, it became clear something unusual was happening with the star itself. One leading theory suggests Rho Cassiopeiae could be on the brink of a supernova, a catastrophic explosion that marks the end of a star's life. In the final stages before such an event, a star's behavior can become erratic, and its signals might fade as internal processes go haywire. It's like the calm before a storm, an ominous lull before the universe delivers its grand finale. Others propose less dramatic explanations. Could a thick cloud of dust or gas have drifted between Rho Cassiopeiae and Earth, blocking its signals from view? Stars like this often shed material in massive outbursts, and if enough debris accumulated, it might temporarily obscure the star's light. Or perhaps the star's own activity cycles have entered a quiet phase, a natural pause in its usual rhythm. But here's the twist: Rho Cassiopeiae isn't just any red giant. It's a hypergiant, one of the rarest and most massive stars in the galaxy. Stars like this don't follow the usual rules, and their silence could hint at processes we've never witnessed before. Some researchers even speculate that what we're seeing isn't a prelude to a supernova, but something entirely new, a previously unknown stage of stellar evolution. Whatever the truth, Rho Cassiopeiae's silence is a puzzle that defies easy answers. It challenges our assumptions about how stars behave and reminds us that the universe always has surprises up its sleeve. And as we move forward, this enigma leads us to our next mystery, a signal from Xi Cygni that seems to stretch time itself. Now, let's unravel another cosmic oddity, one that bends the very fabric of time. The signals from Xi Cygni don't just reach us, they arrive stretched, as if the universe itself hit the slow motion button. Picture a song playing at half speed, every note dragging longer than it should. That's the eerie effect astronomers have observed with this red giant's emissions. So what's causing this time warp? One compelling explanation points to Einstein's theory of relativity. When light travels through extreme gravitational fields like those near black holes or dense neutron stars, it can literally stretch, a phenomenon called gravitational time dilation. If Xi Cygni's signals passed near such an object on their way to Earth, that could explain the delay. It's like rolling a ball up a hill. The steeper the slope, the slower it moves. But there's another contender, the interstellar medium. Space isn't empty, it's filled with sparse gas and dust that can subtly slow down light, especially at certain frequencies. If Xi Cygni's signals traversed a particularly dense patch of this cosmic fog, the journey could have stretched them out. Think of it like walking through knee-deep water versus sprinting on dry land. The medium changes your speed. Here's where it gets even stranger. Some researchers argue the signal's distortion doesn't perfectly match either explanation. Could there be an unknown factor at play? A few daring theories suggest exotic physics, like hidden dimensions or quantum foam. Tiny fluctuations in spacetime itself might be tweaking the signals en route. While these ideas are speculative, they highlight how Xi Cygni's mystery pushes the boundaries of what we know. One thing's certain, this isn't just a quirk of observation. The time-dilated signal challenges our understanding of how light travels across the cosmos, forcing us to reconsider the invisible structures that might lurk between the stars. And as we piece together these clues, we're led to our final enigma, a signal from Omega Sagittarii that defies every rule red giants should follow. Now we arrive at the final puzzle, one that shatters expectations. The signal from Omega Sagittarii pulses at a frequency that simply shouldn't exist for a red giant. Imagine tuning a radio and stumbling upon a station broadcasting in a language no one's ever heard. That's the level of bewilderment this discovery has caused. At first, astronomers assumed it had to be a glitch. Red giants emit light within certain predictable ranges, like a singer hitting familiar notes. But Omega Sagittarii's signal is more like a screech outside any known scale. Initial checks ruled out instrument malfunctions, and recalibrations only confirmed the anomaly. This wasn't static, it was a real, repeating pattern defying stellar physics. Could it be interference from another cosmic source? Some propose a nearby neutron star or black hole might be distorting the signal, like a funhouse mirror bending light. Yet no such object has been detected in the vicinity. Others wonder if we're seeing the aftermath of a rare stellar collision, a cosmic car crash leaving behind debris that vibrates at this strange frequency. Then there's the radical possibility. What if red giants can produce frequencies we never imagined? A handful of theorists argue that under extreme conditions like turbulent magnetic fields or exotic matter in the star's core, new types of emissions might emerge. It's akin to discovering fire can burn colors beyond the usual spectrum, but the boldest hypothesis that we're not hearing the star at all. A few researchers whisper about artificial origins, not necessarily aliens, but perhaps an ancient, unknown astrophysical phenomenon mimicking technology. It's a fringe idea, but Omega Sagittarii's signal forces us to ask, are we missing a whole chapter in the book of stellar behavior? One thing's undeniable. Whether it's a measurement fluke or a cosmic revolution, this signal reminds us that the universe still holds surprises that defy our textbooks. And as we close this journey through 25 unexplained signals, that's the real takeaway: the cosmos is far stranger and far more mysterious than we've dared to dream. And so, as we reach the end of our cosmic journey, let's take a moment to reflect on what these 25 mysterious signals from red giants have taught us. From Betelgeuse's erratic pulses to Omega Sagittarii's impossible frequency, each one defies the rules we thought governed these aging stars. They flicker, vanish, echo, and even mimic patterns that seem almost deliberate, leaving astronomers scratching their heads and rewriting theories. What's striking is how these anomalies aren't just isolated quirks. Together, they paint a picture of red giants as far more dynamic and enigmatic than we ever imagined. Stars like Aldebaran and Zeta Aurigui challenge our models of stellar behavior, while signals from Mira and Delta Andromedae blur the line between natural phenomena and something stranger. It's as if the universe is whispering secrets we're only beginning to decode. But here's the thrilling part: every unanswered question is an invitation to explore further. Maybe one of these signals holds the key to a groundbreaking discovery, a hidden stellar process, an unseen cosmic neighbor, or even a glimpse into physics we've yet to understand. That's the beauty of space mysteries. They remind us that curiosity is our greatest tool. So what do you think? Could these signals point to something beyond our current science? Or are they just cosmic puzzles waiting for the right solver? Drop your wildest theories in the comments below. I'd love to hear which signal fascinates you the most. And if you're as hooked on these cosmic riddles as I am, don't forget to like, subscribe, and hit that notification bell so you never miss our next dive into the universe's biggest mysteries. The stars have more stories to tell, and I can't wait to explore them with you. Until next time, keep looking up.